All right, this is 7.1, properties of the normal distribution, and it has, it's a pretty straightforward section. It's not too difficult, very manageable. Let's get right to it. The notes are brief. Each of the problems I included a printout of the example of it as well in your notes, so this should be a pretty easy section to go through. Let's get right to it. We already have experience with the normal distribution, also known as the normal curve. We are used to seeing it. If you don't recall, it's the one that looks like this. We talked about it in many previous lectures. It's symmetric, it follows the empirical rules, blah, 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 blah. You guys are very familiar with it. We've seen it over and over again. Okay, so let's take a look. The normal curve is symmetric about its mean mu. Is this true or false? This is true. So, and it's in your notes as well. This is true. The normal curve is a symmetric distribution, yep, with one peak, yes, which means the mean, median, and mode are all equal. Therefore, the normal curve is symmetric about the mean mu. There it is, okay? Number 2, fill in the blank to complete a statement. The area under the normal curve to the right of mu equals. So I should probably draw a slightly larger picture to kind of help you get going with this. But maybe we'll kind of do it right over here. So recall that here's your mean. And it's split evenly, half and half, across. And we've done a lot of different pictures and worked through this over the course of the semester. So the area under the curve to the right, so to the right of the mean, or mu, right? That is equal to what? Well, it's equal to 1/2, because we know that the total area should be equal to 1. All the area underneath adds up to 1, because all probabilities which fall within there are between 0 and 1. Okay, let's move on to the next one. Determine whether the following graph can represent a normal density function. Well, the answer is no, because it's not symmetric. It's not a normal distribution look. Okay, so no, that's skewed right. We know that. Determine whether the following graph can represent, well, here's another, same problem, right? So the answer is no. Bottom line is you're looking for something that should look like the normal distribution in order to answer yes. So here is a really good example. There you go. Determine whether the following graph can represent a normal density function. Yes, that can. Why can it? Because you don't have the lines crossing over and down. You might have an example that has that. You don't have a skewed right, skewed left graph. There's a lot of different examples of what it cannot be, but what it can be, and only one, is some version of a symmetric, single peak, mean, median, mode, all the same graph. Okay? Fits the definition that we talked about earlier. Okay, on to number 6. All right, so in number 6, I'm just going ahead and erase this. Okay, in number 6, it says the graph to the right is the uniform probability density function for a friend who is X minutes late. Find the probability that the friend is between 20 and 30 minutes late. So first and foremost, let's go take a look at this. We're looking at part A, taking a look at part A, and specifically they said find the probability that the friend is between 20 and 30 minutes late. Find the probability that the friend is between 20 and 30 minutes late. Well, that means that you need to go do something with 20 and 30. Well, here's 20, here's 30. The way you're going to solve this problem is you need to come up to 20 and note that the probability for 20 is 1/30. Well, it just so happens that 30 is, in fact, all of them. From time 0 to time 30, it just so happens that our probability is 1/30. Now, if you want to know the probability that the friend is going to be between 20 and 30 minutes late, then all you have to do is subtract and find the difference between the two and multiply it by whatever your probability is. That would that would give you your answer. So whatever your problem is, maybe your problem is 5 to 10, 15 to 20, 25 to 30. Whatever it happens to be, you would find the difference in time and multiply that by the probability, which is going to be in there, and all of them are going to be essentially the same. So for my problem, that ends up being 10 times 1 over 30, which is going to be 10/30th, or 1/3, which is, I don't need a calculator for that, round to 3 decimal places. I know that 1/3 is 0.3333 and so on. So 3 decimal places would be simply 0.333. Okay? That's it. Very straightforward. A lot easier than some of the things that we've done before. Okay, part B. So there is a 30% probability the friend will arrive within X number of minutes. Well, in order to do this, you got to set up an equation. Okay? The equation is going to be set up as follows. This right here is what we're searching for. We're going to call that X0. You call it whatever you want to do. Okay? Whatever you want to call it, no big deal. Now, this is basically this time that you're looking for. So you're still going to multiply your time by your probability, because that probability rings true through this entire scenario. And so they tell you that the amount of time times our probability is going to be 0.3. Let me separate these two because they're unrelated, really. I mean, they're just similar calculation, but unrelated problems. So where did this come from? This comes from what you're searching for. You're looking for the time. So the time component. This is your time component. Then 1 over 30th is your probability, your uniform probability. So this is your probability across all scenarios. But the amount of time is going to change the ending probability, and that's what we're actually looking for. So there's a 30% probability, okay, that the friend will arrive this number of minutes late based on this density function's probability. Now, it just so happens these are both 30s. Don't always expect that to be the case. Your problem might not be like that at all. So if your numbers are different, this number comes from here, this number comes from the part of the problem. So with that said, how do we actually get the answer here? Well, it's pretty straightforward. You can divide both sides by that 1 over 30 here, because we're trying to get rid of it, right? And so your amount of time is going to equal, for me, 0.3 divided by 1 over 30. Here's where I rolled over my calculator, okay? So 0.3 divided by 1 over 30. So that's how I typed it in. So 0.3 divided by 1 over 30, and that gives me 9. There's a couple other ways to do it with cross multiplication and so on, some other ways and other things. So what does that mean? Here it is. There is a 30% probability that the friend will arrive within 9 minutes. So based on this model, if somebody arrives within 9 minutes, this model said there's a 1 out of 30 probability of that happening. So the chance of that is 0.3. Okay? So that's the uniform probability, and the chance based on that is 0.3. Done. Okay, next. All right, let's do it for another one, shall we? So we have another density function, okay? And so we kind of have the work from the previous one. Let's take a look here. Graph to the right is the uniform density function. Here's our pieces. Find the probability that the friend is at least 20 minutes late. Well, geez, I actually wish that this was a little bit different problem, because it just so happens that this is going to end up being the exact same problem as mine, because at least 20 minutes late means what? That means at least. The key word is at least. At least means that I'm starting at 20 and I'm ending again at 30, and I have the same exact 1/30th, so I'm literally going to do the same exact problem. I wish this was a different problem. Let's say that it was at least 15 minutes late. Then I would do 30 minus 15. If it said between 10 and 20 minutes late, it'd be 10 and 20. Whatever yours happens to be. So I'm pretty sure that this is going to end up being the exact same answer as we had before. Unfortunately, it didn't give me a new one, but how about I do a similar question? Let me back up and let me see if I can get a similar question. There we go, that's better. So let's do this one. This is a little bit better, shall we? That was not ideal to get the exact same question. So this is a lot better. Okay, so find the probability that the friend is at least 13 minutes late. Well, not much changes. Instead, you've got a different starting point. In this case, it's 13, and you have to go to here. So what do? What is your ending? 30. Yours might be different from mine. What is your starting? 13. Why did we do it that way? Because it said at least. That means I can go from 13 all the way up to 30 this way. And then I'm going to multiply it by the 1 over 30th. Where does that come from? Right there. And then that is going to produce my answer. So 30 minus 13 is 7 times 1 over 30 and whatever that ends up being. Okay, so 7/30ths and whatever that ends up being as a decimal. So 7 divided by 30, and that's 0.2333. Okay, oops. Round to 3 decimal places. Let's see here. Oh, 17. Mistake, not 7. 17. Not paying attention. Let's try that again. 17 divided by 30. There we go. 0.567. All right, there it is. Done with that one. Okay, let's move on. So number 8, here we go. Number 8 says, a study was conducted that resulted in the following relative frequency histogram. Determine whether or not the histogram indicates that a normal distribution could be used as a model. Well, what is a normal distribution? A symmetric single peak. Is this a normal distribution? Remember that the shape needs to look like this and this, or like that. This is a shape that is skewed left. So this is certainly not a normal distribution. So the answer is no. The histogram is not bell-shaped. There's one of them. So a normal distribution could not be used. There's the right selection. The histogram is not bell-shaped. It's skewed left. It's supposed to be bell-shaped. So a normal distribution could not be used as a model. Okay, there you go. All right, number 9. Let's look at this one. So determine whether or not the histogram indicates that a normal distribution could be used as a model. Can it? Well, I have another skewed left one. Yours might be different, but mine certainly is not. So let's go see if we can find the right answer. It's definitely a no. No, because the histogram does not have the shape of a normal curve. That looks pretty good. How about E? Yes, no, it's a no. It's supposed to have a shape of a normal curve, a bell-shaped curve, but it's not. It's a skewed left. Because it does not have this shape, instead it's skewed left. No, because the histogram does not have the shape of a normal curve. In order to model the data after a normal distribution and perform the calculations necessary, it has to look like a bell shape to a certain degree. Okay? All right, let's look at number 10, shall we? So on number 10, we got to reference these two pictures over here, these two different normal curves, and one A and one B. The red is A, the blue is B. Important note that this 7 is the mean for A, and this 13 is the mean for B, okay? So just keep that in mind as you work through your problem. They tell you one graph in the figure represents a normal distribution with a mean of 13. That's this one. And standard deviation of 3. So they say this one has a standard deviation of 3. That goes with this one. The other graph represents a normal distribution as well with a mean of 7. Here's 7. And a standard deviation of 3 as well. So this red one, for me, they both happen to have the same standard deviation. Great, whatever. Okay, that doesn't have to be the case necessarily. Okay, determine which graph is which and explain how you know. All right, so let's look at our options. A, graph A has a mean of 7 and graph B has a mean of 13. Yes, that looks like it matches. because a larger mean shifts the graph to the right. And that's true. So that might be an option. Let's go to B. Graph A has a mean of 13. No, graph A is 7, so that's out. We don't even have to read any further. C, graph A has a mean of 7. Yes, and graph B has a mean of 13. Yes, because a larger mean shifts the graph to the left. No, the larger mean is to the right, so that's wrong. All right, last one. Graph A has a mean of 13 and graph B has a mean of 7. That's wrong. So the correct answer was which one? A. Graph A is the following, all those details. So I hope that makes sense. There you go. Okay. On to number 11. All right, so on 11, we've got another normal curve that we need to do a little bit of interpretation on. I don't know if I can zoom in much. Nope, let's stay back. The graph of the normal curve is given to the right. Here it is. Use the graph to identify the values of mean and sigma. Okay, so what is this? The one in the middle, this right here, what is that one? That's your mean, right? So our mean is always the one in the middle. We've seen that in multiple problems. It was kind of discussed right from the get-go in words as a word definition. Now, the standard deviation, you should know that. We've been doing this all semester long. The 16 and 22 represent one standard deviation out from the mean. The 13 and the 25 represent two standard deviations out from the mean. 10 and 28 represent 3 equal standard deviations out from the mean. So all of these should have the exact same spacing, and that exact same spacing should be symmetric on both sides of the mean on this bell-shaped normal curve. And so our standard deviation should be the exact same increments all the way through. What is that? Well, you could subtract any one of these pairs and it would give you the answer. And so that would be 3. So I've done that where you can clearly see that standard deviation is 3. The spacing is 3 for all of these. Okay? So that means our standard deviation is 3. Okay? All right. Let's move on to the next one. Almost done. This is, like I said, it's a very straightforward section. Okay, suppose the monthly charges for a cell phone plan are normally distributed with a mean of 58 and standard deviation of 19. Draw a normal curve with the parameters labeled. Okay, so that's part A. Let's just do one part at a time. If we know that the mean is 58 and the standard deviation is 19, in other words, the spacing between each standard deviation is 19 units up or down, then we should easily be able to pick out the correct answer here. So what am I going to do here? Well, I'm going to go first find the graph with the middle right at the peak being 58. I'm going to eliminate any others that aren't that. Out, peak is 77. Out, peak is 39. 58, 58. That's pretty good. Both of these are options. Now, how would I determine whether to pick C or D? Well, from the previous problem, you learned that a standard deviation of 19 should mean that the difference between our units, our cutoff points, whatever way you want to call it, our standard deviation markers for the first standard deviation should add up, or the difference should be 19. Well, clearly D is not that. This, C, is the correct answer. So C, the difference is indeed 19, and so there it is. Okay? All right. Let's move on to the next one. So for part B, it says shade the region that represents the proportion of plans that charge less than $39. Okay, so what you should do is do what? You should pick up where you left off from the previous answer. So 39, 58, 77, that should help you eliminate some answers. 39, 58, 77, those are wrong. 39, 58, 77, okay, that's a good start. 39, no, no. So without even having to do any work, I just actually answered the question. But let's just be a little bit more specific and answer this and understand why this is the correct answer. Shade the region that represents the proportion of plans that charge less than the 39. There's 39. Less than that is this region, and that's why B is the correct answer on top of eliminating the others because they just didn't match up with what we had before. Okay, last part, C. All right, C says, suppose the area under the normal curve to the left of x equals 39 is 0.1587. Provide an interpretation of the result. So what they're saying here is that, recall that this was the correct choice from before. They're saying that this area, the probability of that is 0.1587. That's the probability of obtaining something, a cell phone plan, less than $39 given this structure, okay? So how can we kind of restate that? Let's look at A. The probability that is 0.1587 that a randomly selected cell phone plan in this population is more than $39 per month. No, less than. This corresponds to less than, so it's not more than. Let's look at B. And that's gonna mess me up. It's probably B here. The probability is 0.1587 that a randomly selected cell phone plan in this population is less than that $39 per month. And that is the correct answer and proper interpretation of what's going on there. Okay? All right. Let's go to the next one. Okay, so suppose the birth weights of full-term babies, this is going to be one just like before. Suppose the birth weights of full-term babies are normally distributed with a mean of 30,550 grams. There you go. And obviously they say normally distributed, so these are all, bell-shaped normal curves. And a standard deviation of 515 grams. We're going to do the exact same thing that we did in the previous one. Let's go through the parts. Let's match the curves. So we better see a line in the middle that represents the mean at the peak of 3550. Wrong. Good, good, wrong. So those two are out. B and C are remaining options. Now the standard deviation is going to help us determine it. The difference here should be what? 515, 515, and all in these brackets or in these cutoffs, in ranges. So which one is 515? Well, not this. That's wrong. Those are wrong. B is the correct answer. So there it is. B is the correct answer. And now we're going to go to our shading. But before we go and start shading, I don't even have to answer the question. I first can do some elimination just knowing my correct answer from the previous problem. Correct answer from the previous was what? It was B, right? So I better have the numbers 30, 35, 35, 50, 40, 65. So these are the numbers that should come right down, and then we would shade accordingly. 35, 50, wrong. 30, 35, 35, 50, 40, 65, good. Wrong. Wrong. I don't even have to do any work. There's the correct answer, but let's shade accordingly. Shade the region that represents the proportion of full-term babies who weigh more than 4,580. Well, let's go scoot over here, and there it is. There it is. So notice how the numbers matched up. It looked a little off, but sure enough, yeah, 4,580 grams is way outside the first standard deviation. So it's all the way over here, which makes total sense. This is wrong, that's wrong, because they didn't take into account the correct numbers. And greater than shades that region. That's perfect. That's the correct choice. All right. So I'm going to kind of slide this over here so we can interpret this. All right. So let me erase so that we can see this easily. Let's do the interpretation. Recall that this is what we're focused on. The probability is 0.0228 that the birth weight of a randomly chosen full-term baby in this population is more than. That's the right wording this time around. Not less than. More than is this way. Less than is this way. So this is out. And more than 4,580 grams. Okay? There you go. with one more problem to go. We're doing great. Okay, so final problem is number 14, and this is actually really similar to what we did before, so I'm going to leave that for you to do, and that'll do it.